the certification authority that signed either party's ticket. So it's that signed Bob's ticket, and that Alice is assuming as she as she forms this encryption message. Okay. In other words, we need an encryption scheme such that when I form a public key from a certification authority that is in my policy, nobody should see that. So nobody should seeing this ciphertext, okay? Because this is going to be a ciphertext, right? Nobody should be able to link that ciphertext to the certification authority that Alice was using in forming it. And similarly, you see, because it's an interaction, Bob is going to perform this interaction on his input of a ticket that was signed by CA2. Again, nobody seeing this interaction should tell what is the authority that signed Bob's ticket. And this is the secrecy property, but of course we need, this to be a strong encryption, right? Because in particular, Alice encrypts her proof of possession of a certificate. So if there was another way of decrypting this but the position of the signature, then then the information that she's associated with CA1 would leak. And this is a funny notion of encryption that is secure against chosen message attacks, okay? And from which you basically, so it sounds like signature security really, and not surprisingly, because it's an encryption derived from signatures. I will actually explain this notion right away. Okay, no, but first I will do the explanation of how do we state and prove affiliation hiding of this encryption. So what is affiliation hiding? First, we have two types. So we have an affiliation hiding for the sender. Alice starts from input of CA2, and she forms this encryption. The verifier, the receiver, might be a malicious person whose aim is just to tell, is Alice affiliated? Is Alice the type of person who accepts conversations with people who are affiliated with CA2? And if the conversation that Alice presents to the verifier is indistinguishable from the conversation that can be produced on just public parameters. So for those of you who are acquainted with the cryptographic terminology, this machine on the right is called simulator. So the simulator, just knowing the public parameters, not knowing anything about the certification agency that is in Alice's policy, if the view of the protocol that the simulator can produce is in fact indistinguishable from the true Alice, so even a malicious receiver cannot tell the difference between the two, then clearly for cryptographers, this conversation must not leak, must be leaking nothing about this Alice's input, okay? Because you can do the same conversation without knowing the input. And a similar notion for the receiver. So now the Alice can be malicious, and however Bob participates in this protocol, he starts on an input the ticket from CA2, okay? And again, and here, if we think of it as an encryption, his participation is very passive. So what are we talking about? Well, this is an interactive encryption, or it could be, and it is in our case. So his participation in it will indeed be based on his inputs, and therefore the problem stands. And we define the notion in the same way. If a simulator, not knowing any tickets, and in particular not knowing that Bob, what certification authority is issuing these, can produce a view that looks the same, that's our notion of affiliation hiding for the receiver. Okay, and and a chosen message attack on a signature scheme Well, so recall what is a chosen message attack on a signature. Okay, sorry. I will flash the notion of chosen message attack security of this encryption I'm building. So here is the chosen message attack security of a signature. Adversary gets any message that he wants signed, okay, and he does it repetitively. So he sees signatures on any message that he wants, and he wins the game if he can issue some unsigned message and a signature on it that is forged because it's not any of these. Okay, so we say signature is chosen message attack secure if such game cannot succeed. Okay, if no adversary can succeed in this game. Similarly, for this encryption scheme, adversary, in this case the malicious receiver, he perhaps he gets a lot of trapdoors for many pseudonyms. Okay, and so he gets many trapdoors for many pseudonyms. But let's say that these are all pseudonyms of bad people who are revoked. Okay, so now in order to pass through the protocol, he has to issue a different pseudonym, not on the list of the revoked group members. And now he has to pass in the following game. Alice picks some message, she sends it over, encrypted under the CA and this new pseudonym, and Bob, or malicious verifier, wins if he can decrypt it. So it's very similar to security signatures. In signatures, he won if he could output a new signature on unsigned message, and now he wins if he can, on unsigned pseudonym, he can decrypt on the key that corresponds to the unsigned pseudonym. So let me just point out that this is exactly what so identity-based encryption is precisely this. Okay, so it passes this notion, because if you think of these trapdoors as private keys, these BIs as identities, and the trapdoors as private keys on those identities, this is exactly what the security of identity-based encryption says. If you present some identity that is not yours, so you don't have a trapdoor on it, you should not be able to decrypt. Okay. Also, standard PKI can be taught in this as an example of this setting, but we skip that. Okay, so let me just go quickly. This will be 3 or so minutes of more technical thing. The construction of this anonymous encryption from discrete log signatures. So discrete log signatures, the secret key is of the authority that signs these trapdoors is X. Public key is G to the X. And a signature on some message in our application pseudonym is a pair, SR, which satisfies this equation, okay, where H is a hash function. So the adversary gets a lot of these, gets signatures on some pseudonyms. Now all those pseudonyms are revoked, and so he. So this is the interactive encryption. Excuse me. He sends. Excuse me. Actually, you know what? Why don't you look here first?